This is the repeat of the stream that was supposed to happen last week, but something exploded and it didn't work. So I will go over the notes, point out all of the important aspects of 8.4, which is on divergence integral and P-series tests. So we are working on three different tests. Well, actually, two of them are the same, integral and P-series. P-series is just a special case. We'll see that. So we'll start with the divergence test, and the most important part here is to understand the words divergence, right? So this test can only be used to show divergence. It cannot be used to show convergence. Divergence test states that if the limit of the sequence an within the series is different than 0, then the series diverges. So it's a very important definition. It's extremely easy to use as long as the limit of the sequence within a series is different than 0. Immediately the series will diverge. And here are a few introductory examples. So we know n squared, right? Series n squared will diverge because the n squared goes to infinity. We also have a faster growing, second example, faster growing function divided by the slower growing function. So we have factorial divided by polynomial. It will be again divergence because the limit goes to infinity. And the last one is the one that I'm asking you now to memorize by the end of this section or this lecture. You will know why and how. And that's harmonic series, very important. Harmonic series 1 over n. Now this is also a great counterexample because this is the one that shows that a series can diverge even if the sequence converges to 0. So we cannot make any conclusions about a series if the sequence goes to 0. In that case it can swing either way, but if the limit of the sequence an is different than 0, then the series would definitely diverge. So just be careful which way you look at the problem. Now, also very important here is to learn that divergence test is the easiest one to use, and you should always try that first before you start working with any other test. So I remember that in class, I'll write it here again. In class I mentioned, and I think I wrote it on the board, a series of, let's say, 5 to the k. This is a geometric series. If it starts at 0 and goes to infinity, and you know this one diverges by geometric series, but then you can also say by divergence. Before you even consider geometric series, you can just say, well, limit of 5 to the k as k goes to infinity is infinity, which is different than 0, therefore diverges by divergence test. However, you can also use the geometric one for that. All right, let's talk about integral test. So integral test is probably the longest of all tests to perform, and also probably the most annoying one because there's a lot of things that we have to do. We will be changing the discrete function an into a continuous f of x, and we can establish the equivalency between the convergence of the integral and the convergence of the series if the three conditions are satisfied, namely that f of x is continuous, positive, and decreasing. Now that's what makes this procedure long. You first have to prove all three conditions in order to establish the correspondence between the convergence or divergence of series and the integral. And then once you're done with those three mini proofs, let's call them, you would have to do the improper integral and check for convergence or divergence of the integral to see what's happening with the series. So we start with 1 over n, which is harmonic series. So that's the first example. And the first thing we do is we change the discrete function 1 over n into a continuous 1 over x. Now we have to prove those three conditions, continuous, positive, and decreasing, and only if all three hold we are allowed to use integral test. Now, in order for us to prove those three conditions, we take a look at our function and we look at the graph. Now, looking at the graph, we can actually see all three features right away. We see that the function is continuous on the domain, right, 1 to infinity, because we only care about 1 to infinity. You see that we start at 1 and go to infinity. So on that part, 1 to infinity, the function is perfectly continuous. We also see that it's decreasing and it's positive, positive meaning above x-axis, so all the y values are positive. Once we are done with that, we move to solve the improper integral. We have the improper integral 1 to infinity 1 over x dx, and we introduce limit, which is the standard procedure in solving the improper integrals. The integral of 1 over x is integral of 1 over x is ln x, so ln absolute x, and then we plug in the limits, which we get the divergence. Now the actual answer is what is written in red, which is which states, because the integral 1 over x dx diverged, the series 1 over n diverges as well by integral test. So the procedure is to prove all three conditions first, that the f of x is continuous, decreasing, and positive. Once those three conditions hold, we know that both integral and the series will do the same thing, namely both converge or both diverge, and then we will perform the integration, the improper integral, and then whatever we get at the end is the answer. So here is another example. Now this is 1 over n squared. Again, start with a discrete function, create a continuous one, and then since we also know the graph for 1 over n squared, we can graph it and just look at the graph and find that on the domain that it's asked, which is 1 to infinity, the domain that we are looking for is going to give us continuous, positive, and decreasing. Again, we will do the integral from scratch, and this time we are going to get convergence, because once we do the computation of the improper integral and apply the limit, the first 1 over b part goes to 0 because it's 1 over infinity, and then we get the answer to be 1. So now the actual answer for our question is that since the integral converged, the series converges as well by integral test. Now it is extremely important to understand that when the integral converges, series will converge as well, but not necessarily to the same value. Actually, almost never to the same value. So what we do is we know that there is a convergence, but we don't know which number the function converges to. So just make sure that you say it converges, and that's it. We don't actually know which value it converges to. Just want to check if the stream is moving along. Yes, great. Alright, so now here's a little bit spicier example, one where we can't just readily draw the graph and say, oh, okay, it's easy. So the first thing what I do is start at 2, go to infinity, so our domain is going to be 2 to infinity. So on our integral we'll have 2 to infinity if all three conditions hold. We create, looking at the discrete, right, we create the continuous function, and then we start checking the conditions. In terms of continuity, we can use the theorem from Calculus 1 stating that all polynomials are continuous, that ln x is continuous, so combinations of continuous functions are also continuous. The only problem point that we might have here is 0, but we are on domain 2 to infinity. And another one is 1. Again, we are on the domain 2 to infinity. So none of those problematic points are in our domain. Therefore, we can claim continuity on the 2 to infinity. Positive, well, ln x is always positive, and k, which is in denominator, multiplying ln x squared, is also, sorry, x, which is in front of ln x squared, is only allowed to take on values 2 and higher, which means positive. So now you have a number that is square, is always positive, x that it can be taking numbers 2 and more, which is also positive, and you have 1 in the numerator. So 1 divided by the product of two positive numbers is altogether positive, so function is always positive. That's a quick one. And then we have the decreasing. Now decreasing you can do in a few ways. You can actually go and use the comparison from the discrete part, where you show that k plus 1 term is always larger than a kth term, well, kn term. So you can do that, or you can simply take the derivative of the function and check that it's negative across the domain that it's given to you. So in this particular case it was easy because it was 1 divided by some kind of a function that it's increasing, so because both x and ln x are increasing functions, therefore when you divide a number by a larger number, the value decreases as the denominator grows. So that was a very fast way to show how this function is also decreasing. So now that we have all three conditions satisfied, fulfilled, we can quickly do the improper integral. So we'll go this time from 2 to infinity because of the requirement of the series. We will use u substitution, so u equals ln x, because we have 1 over x dx available for du. So we have 1 over u squared, which when integrated becomes negative 1 over u. Plug in all the values to get 1 over ln 2. So again, the integral converged, therefore for our answer we can say that since the integral converged, the series converges by integral test. One more time, we do not know what the series converges to. Integral converges to 1 over ln 2, however series can converge to any other value. Doesn't necessarily have to be 1 over ln 2. So make sure you don't say that it converges to 1 over ln 2. The only two tests that we can use and then have the actual sum at the end are geometric series test and telescoping. So those are the two where we can find where they converge, where the series converges to. P-series, it's a special case of the integral test. It's like a shortcut. So all we have is the series that looks exactly like this. So 1 or whatever constant over k to the p. And these are the two conditions. If p is larger than 1, we have convergence. If p is less or equal than 1, we have divergence. Note that p equals to 1 is the harmonic series, which we already proved that it's divergent. And then there was also p equals to 2, which showed the convergence. That was just verifying one case, it's not a proof. Here are the three examples, right? 1 over k cubed, p is equal to 3, we have convergence. 1 over k to 1.6, p is 1.6, again larger than 1, so convergence. And then k cubed can be written as 1 over k to the negative 3, p is negative 3, less than 1, therefore divergence. So these are the very fast examples, because P series is just memorizing what is the value of P and possibly remembering that you might have to switch the way it's written in order to fit the requirement of how P series looks like 1 over k to the P or 1 over n to the P, depending which variable like to use better. So that covers everything for the section 8.4. We have two more sections left, 8.5, which will cover root ratio and comparison tests, and then 8.6 that will cover alternating. Those will happen this week, and chapter 8 will be behind us. See ya around.